Okay, the last time we were studying the characteristic polynomial of a hyperplane arrangement. So, and in particular, yeah, so maybe I should state the definition is this characteristic polynomial is you look at the intersection lattice of your hyperplane arrangement, and then you sum t to the, you take the Möbius function of x times t to the dimension of x. And in particular, there is a theorem due to Zaslavsky which tells you that the specialization at -1, more or less like up to a sign, gives you the number of regions of the hyperplane arrangement. And if you plug in +1, then you get the number of bounded regions of the hyperplane. And I was trying to explain some steps towards the proof of this theorem. And basically, the proof is that all of these things satisfy the deletion-contraction recurrence. So the lemma that I mentioned last time was that if you have your hyperplane arrangement and you choose one hyperplane, then there are three statements. The first one is that the characteristic polynomial is, so you either remove a hyperplane, right, that's deletion here, minus you contract hyperplane, the same hyperplane. And that means you just intersect all of your other hyperplanes with this one. So you get a smaller hyperplane arrangement here. And this is true for all hyperplane arrangements. And the second claim is that the number of regions is just the sum of the two. And the number of bounded regions is a little bit tricky. So it's either the sum of the two or 0. Or 0. Sum of the two if removing the hyperplane does not change the rank of your arrangement. If A minus H0, same as the rank of H, the rank of A, and 0 if this rank is different. They either differ by 1 or are the same. Hold on, this is one. Okay, so can somebody give me an example of when the second case happens? Coordinate arrangement. Okay, interesting. Okay, so you're saying if A is this, and then one of the hyperplanes is H0, then A minus H0 is which, so how many bounded regions? B is 0, and here 0. And what about if I contract? I also get 0. Yeah, I get a dot on the line, which is okay. Can somebody give me an example where this case still holds, but these numbers are non-zero? Say again? Oh, you want to add a diagonal thing here. Okay. And what is H0? Take it back. Okay. Tic-tac-toe. Oh, you want me to take another parallel line. So you want me to take 2 by 3. And what is H0? The bottom horizontal line. Okay. So if I delete, I get this. if I contract, I get this. What is the number of bounded regions? 2. Okay. Oh, okay, so you want to take, yes, so this is actually the first example of the first case where the rank is just the same. But if I take, indeed, if I take 2 parallel lines and 1 crossing them, and if that's H0, then if I remove, the rank actually drops. Here the rank is 2, but it becomes just 1. And if I restrict or contract, yeah, and so the number of bounded regions here, 0, here. Oh, okay, so is it 1 or 0, or is it undefined? Right, so the so B of A, by definition, denotes the number of relatively bounded regions, always for us. Yes, in particular, it's defined for all hyperplane arrangements, regardless of the rank and the dimension. So in this case, it's actually 1. This is also. So yeah, that's the second case dilemma. And so I'm not going to prove dilemma, but proof. Well, the hardest part is the first case, because we have this definition with the Möbius function. So for the first case, there's actually a lot of stuff going on, so technical. And if you want to see the proof, which you probably should, you can read it in Stanley's book. A few pages long. There's some nice theory. You have to develop some nice theory of like Möbius inversion formula and stuff like that. Yeah, what about, let me address the second part. That's maybe, I'm only going to do easy parts here. So what is the argument for the second part? Yeah? I see. Yeah, that's actually a nice argument. Well, there's one problem because we want it to work for arbitrary dimensions. Right? If you think of hyperplane, it doesn't really start anywhere. You can't really trace it in old process. Yeah. Right. So by definition, to get the relatively bounded region, you have to take the essentialization, which yeah. So essentialization means you take the kind of. So here, this essentialization would be you take the intersection with like this hyperplane here, so you would get a bounded region. And so this strip here is relatively bounded. And yeah, all right. So indeed, there is a way to make this work in arbitrary dimensions, and the reason is basically somewhat simple. So you look at your H, and so H is subdivided by these other hyperplanes into regions. And each of these regions is, if you look at two sides around this region, you get two different regions of A. So if you remove H, these two regions are going to become the same. For any region of H0, you kind of smoosh together two regions of A. Yeah, I know that doesn't sound like too rigorous, but it's actually, there's a pretty simple topological argument that these two things on different sides of a plane are always different regions, and etc. So yeah, anyways, let me just write down number of regions of when you contract is exactly how many new regions H0 adds to A minus H. That's basically simple reason. And finally, yeah, the third part, let me just say that it's analogous to the second. Although there is more work involved in this one, but basically the idea is sort of analogous. All right, and right, why is there the second case? And the second case is there because of our definition of B. B is number of relatively bounded regions. In particular, depending on whether the rank drops or not, you have to use different notions of bounded. Okay, so let me now mention, because at some point I mentioned that things for zonotopal tilings can be proved using deletion-contraction recurrence. Let me just briefly mention what happens for vector configuration. So let's say you have a vector configuration, v1, vn, inside r to the d times n. Yeah, then I wanna, or maybe, yeah, let's say, let me even do it like this. V goes from 0 to n. Then let's say I want to contract v0, or I want to remove v0. What are the definitions for deletion? And here I'm allowed to have like equal vectors, or some vectors may be 0. What is deletion? Okay, remove a vector. Yeah, I mean, these are just labeled. So let me say that if v minus v0 is just v1, etc., vn, just a smaller collection of vectors. And what is contraction? Project along orthogonal projection. Yeah, that's very nice. And here I have to assume that v0 is non-zero. And then contracting is phi of v1, etc., phi of vn, where phi it projects rd to the orthogonal complement of v0, just the orthogonal projection. So, and then, well, okay, so maybe even if all these vectors are generic, or maybe, yeah, let's say there is some other vector is parallel to v0. Right, and what happens after I project? Right, so even if you assume that all of these are non-zero, after you contract, some of them may become 0. And if something was 0, then it still is 0. So easy. Yeah, and the picture you should think of in terms of zonotopal tilings is, I guess I'm going to explain it precisely later, but if you have a, let's say, a fine zonotopal tiling, okay, maybe this is v1, v2, v3, v4, then you can tell, yeah, choose a vector that I should contract or delete. v1. Okay, yeah, v1 is actually easy. Yeah, let's do v1. So I have v1, and actually there is a whole bunch of vectors which are parallel to v1. And then I have a whole, if I look at all tiles which contain v1 as one of their tangent edges, then I have this subtiling. And I can either remove all of these interior tiles, and I get just a, yeah, so sort of, in general, this is going to be a blue strip subdividing my zonotopal tiling into 2 parts. So if I smooth them together, I'm going to get a smaller zonotopal tiling. And that smaller zonotopal tiling is, here I'm the zonotop of V. Here I have the zonotop of V minus V1. And if I instead contract, so I project everything project all the other vectors orthogonally onto orthogonal to V1, then I have so I should think of the result as some kind of zonotopal tiling of a smaller zonotope. The actual, so first of all, what happens if I project my vector configuration orthogonally to V1? Then I get just 3 vectors which look like this. V2, phi of V3, phi of V4. So my zonotope is going to be a line segment. And the corresponding zonotopal tiling is just going to give me, it's just going to be obtained. So I take each tile and I kind of, I just project along the edge parallel to V1. Corresponding zonotopal tiling is going to look like this. And somehow the number of tiles here is equal to the number of tiles here plus the number of tiles here. Yeah? Oh, okay, let's do V4. Yeah, that's okay, let's do V4. That's interesting. I wanted to delete V4, which is here. And so I have all these vectors parallel to V4. So I have this whole, by the way, these things are called zones. I have this zone corresponds to V4, and if I delete V4, then what happens is that this tile here gets glued to these 2 tiles here. So what I get is a picture like this. And if I contract, then I still get, so contract, I still get. And so this is how you can prove that the number of vertices is the number of independent sets, is the number of top dimensional tiles, is the number of bases of your vector configuration. That's the kind of idea behind that. All right, so any questions so far? No questions. Now let me try to, so the next thing I'm going to do is I'm going to compute 2 generic examples. And the first generic example is hyperplane arrangement in general position. So let's say you have some hyperplane arrangement A. And I'm going to say that this arrangement is in general position. If basically if you take any set of hyperplanes and you intersect, then the dimension of the intersection only depends on the number of hyperplanes. So if and I mean it's predictable number. So for any set of H1 up to HP, any P hyperplanes in A, for all such collections of hyperplanes, we have either one of 2 things. Either the dimension of the intersection is equal to n minus p. This happens only if, wait, what is n here? Okay, it should be d minus p. If P less than or equal to D, and same intersection should be empty otherwise. P bigger than D. All right? So, and you should think of generic as actually generic. No two hyperplanes are parallel. No hyperplane contains a line. Yeah, anyways, there's. So any, any D of them. So if you take D hyperplanes in RD, they should intersect at exactly 1 point. So it's a 0-dimensional. So this is always in a affine space. And if it's 0-dimensional, it's just 1. Yeah, so basically, just a bunch of generic random, you can think of these as random hyperplanes. And of course, what I want to do is I want to compute what is the number of regions is 3 here. Oh, sorry, number of bounded regions is 3. The number of all regions is whatever, 1, 2. Number of regions is 11. So I want to find a formula for the 3 and the 11. Yeah. So actually, yeah. So if P is D plus 1, then this is empty. If P Wait, hold on. So if I have 2 parallel hyperplanes in R2, then I have a problem with this condition. So if this is H1, H2, then the dimension of the intersection should be 0. Okay, still. So this is, if still I can take any subset. So I take a subset of these 2 hyperplanes. This is any, I'm labeling them by 1 up to P, but these are just any P hyperplane. Okay, so I want to find the number of bounded regions, number of regions, and the number and the characteristic polynomial. So here's the result. And as you know, it only suffices to find the characteristic polynomial, because the rest is easy. Let's say A is an arrangement inside R to the D, and it contains M hyperplane. Then the characteristic polynomial of A, assume that A is generic. Then the characteristic polynomial does not depend on anything else. No matter how if you draw any 4 random lines in the plane, there's going to be exactly 3 bounded regions and exactly 11 regions. And in general, the characteristic polynomial is yeah? There's a question? Yeah? Yeah, the pole set we get is the same, yeah, and that's actually going to go into the proof. So we're going to see exactly what the pole set is. Minus M to the D minus 1 plus M choose 2 to the D minus 2 minus etc. plus or minus M choose D. So it's like a truncated binomial formula. And yeah, I guess maybe I should. So what's the example here? D is equal to 2 and M is equal to 4. So what do I get? Maybe somebody can tell me. Plus 6. Okay, very nice. Thank you. And let's see. If I plug in -1, I get 1 plus 4 plus 6. That's 11. If I plug in 1, I get 1 minus 4 plus 6. 3. All right. Okay, proof. And I'm going to prove it by definition. So far, we don't have any other, well, we have deletion-contraction, but I'm going to just use the definition. So what is the intersection pole set of my hyperplane arrangement? Nice. Yeah. Okay. That's exactly right. So the intersection pole set is what is called the truncated Boolean lattice, and by that I mean just take all sets of size at most d. I guess L of A is the set of all is isomorphic as a pole set to the set of all subsets of bracket M, where M is the number of hyperplanes, such that the size of each subset is at most d. Okay, and okay, now what is the, if I take an element of this pole set, what is the Möbius function? I see. Yeah, very nice. So for the entire Boolean lattice, what was the answer? -1 to the cardinality of S. And why is this still true for the truncated Boolean lattice? Okay, yeah, because the Möbius function only depends on the things below your element. So, and the things below form just an honest Boolean lattice of this. So yeah, now you just take the sum, right? You sum, these are the coefficients, and e to the dimension, which happens to be, the dimension is predictable from this formula here. So the answer is A of t is the sum over all subsets of bracket M of size at most d of -1 to the size of S times t to the dimension, which is d minus. And that. Any questions on this proof? So yeah, now I want to do some other generic example. So everybody's going to be confused because there's two different notions of generic. So here's another. I mean, these are both very natural. So let's say you have some vector configuration. V1 all the way up to Vm. Vm. And let's say I want to take their, so I'm going to assume that the only thing I'm going to assume is that Vi, each vector is non-zero. I'm going to allow multiplicities. And then what I'm going to do is, I'm going to choose some numbers, A1, etc., all the way to up to Am, just some real numbers. And consider an arrangement of hyperplanes, which is of the form, so let's say each given hyperplane Hi is the set of all y in R to the d, such that the dot product with Vi is equal to Ai. Okay, so I take the normal hyperplanes and I shift them by some amount. For each hyperplane, I choose a shift, and we say that this tuple of numbers is generic if basically the same condition is true. So let me write it down this way. If for all, because here I can have parallel vectors and some, this is very different from that generic over there. Here I can have, yeah? Yeah, if you have three planes in R2, then they have the empty intersection, which is okay. So this collection of shifts is generic with respect to this given V configuration, if and only if for any set of hyperplanes, the corresponding intersection is non-zero, is non-empty, if and only if I is an independent set. I don't know if you remember this notation, but this means that vectors in I are linearly independent. So basically, you can take maybe, yeah, let's do an example. Let's say V is, let's say, I have two parallel vectors, V1, V2, and then maybe V3 and V4, something like this. Then I shift, basically I take each hyperplane and shift them randomly. So for V1 and V2, the two hyperplanes are going to be parallel. For V3, it's going to look something like this. And for V4, it's going to be horizontal. Maybe, oops, horizontal. That's fine. Yeah. This is generic shifts. Well, people can't see. Okay, let me do it here. This is generic. Because let's say I take, so this is for 1 and 2, and then this is 3, this is 4. If I intersect 1 and 2, I get an empty set, because V1 and V2 are not linearly independent. Yeah, if these vectors are linearly independent, then you definitely get a non-empty intersection. So, and the claim is that no other, yes, so let me give you another example. Maybe I should do this, and so is this generic or not? No, why not? Okay, I have three hyperplanes intersecting, 1, 2, and 3, but V1, V2, sorry, hold on. 1, 3, 4, yeah, but V1, V3, and V4 are not linearly independent. This is not generic. Okay, so I have a different notion of generic, which is defined for any given vector configuration. And now I want to compute the number of regions and the number of bounded regions and the characteristic polynomial. So you want to find a linear condition on the A's so that which guarantees that it's generic. Yeah, and I think the answer should be that for any circuit of your vector configuration, something should be non-zero for A. Yeah. This can be, the set of generic tuples is basically a complement of some hyperplane arrangement as well, which is called the secondary arrangement. Anyways, so let me continue. So proposition. Let's say I have a vector configuration and a collection of shifts, and the corresponding hyperplane arrangement, let's assume that these are as above, as on that blackboard over there. So in particular, I'm assuming that these are generic shifts. Then what I want to say is, I want to find the number of regions, number of bounded regions, and the characteristic polynomial, which, by the way, so let me try to draw that example again. What's the number of bounded regions? 2. What's the number of regions? 10. Okay. So what is it going to be in general? What is 10 in general for an arbitrary vector configuration? You should think of 10 as almost 11. It's 11 minus 1, which that's the number of independent. Yeah, that's the number of independent sets. So it's pretty cool, right? Because there is one pair which is parallel. So otherwise you would get 11. Here you get only 10. So yeah, that's the first claim is the characteristic polynomial of my hyperplane arrangement is the sum over all independent sets of -1 to the size of I times t to the d minus the size of I. And the number of regions is just the number of independent sets. And the number of bounded regions is whatever you get by plugging in t equals to 1, this formula. So it's the number of you take the difference between the number of independent sets of odd size and number of independent sets of even size. That's the number of bounded regions. Sum over all independent sets of just -1 to the size Okay, how do I prove this? I'm not actually going to prove this, but I mean, okay, how do I prove this? If you look at this formula, yeah, that's actually, so by definition, basically, each independent set, each non-empty intersection comes from some independent set. Any subset of an independent set is independent, so you get, again, some sort of truncated, it's not a truncated Boolean algebra, but it's some sort of lower order ideal in the Boolean algebra. So the Möbius function is still -1 to the number of elements. That's basically, which, yeah, and by the way, you've seen this formula before, right? What is this number? What is some other interpretation of this number? Unimodular. Yeah, actually, for the unimodular, we had the number of bases. The volume was equal to the number of bases. But the number of independent sets, we have definitely seen before, right? Okay, it's number of vertices inside any zonotopal tiling. So, and that's actually, that sounds like a coincidence, maybe. You know, is it a coincidence or actually? Yeah, let me explain the reason why this is true. So remark. So let's say you have a V vector configuration, then so if you fix the vector configuration, then you can get many different generic tuples. If the hyperplanes in many generic ways, and you get a whole bunch of different hyperplane arrangements. And the claim is that, so for a given V, which is fixed, the duals of such generic hyperplane arrangements are precisely what? This may or may not be hard to guess. If I take a generic shifts, and then I take the sort of, I want to take here, I'm going to take the planar dual, but in general, so as you know, the regions correspond to vertices of any zonotopal tiling. Yeah. So are precisely what? Yes. So what do I mean by dual? By dual, I mean here you take your original arrangement, it subdivides the whole space into regions. For every region, you can take the faces of that region, so I get some sort of face lattice of all possible regions. And when I take the dual, I want to just flip that lattice over. So I want the vertices of the dual object to correspond to the odd-dimensional regions of my object. I see. So you want to take the zonotope of V. The whole thing is the zonotope of V. That is definitely true. But then we have some extra data, right? We not only have we have the whole zonotope, but we also like all these vertices and yeah. The question is what's the continuation of this sentence? Which yeah, I mean I know. By the way, I should mention I know that I'm being sort of annoying, asking you guys to guess all the different things, like what's the next theorem that I'm going to say, and then you're supposed to guess. But I believe that's actually a pretty efficient way to teach. When you read the book, you should close the next theorem and try to guess what it's going to say. That's actually pretty works remarkably well. So yeah, anyways, nobody has a guess. Well, okay, right. So the dual has to be a zonotopal tiling. The dual is a zonotopal tiling of this zonotope is the answer, but not quite. The actual answer is that what you get is a precisely all possible regular zonotopal tiling. Precisely the regular fine zonotopal tilings of the corresponding zonotope. Yeah, so I take A's to be all possible generic, or maybe even non-generic for that matter. You just get non-fine. You should just get all regular zonotopal tilings, which are not fine. So yeah, in particular here, remember I mentioned before that in 2 dimensions, the regular fine zonotopal tilings are dual to pseudo-line arrangements, which are stretchable. For any zonotopal tiling, you can draw pseudo-line arrangement. Something like this. And do you remember that or no? Okay. Yeah, okay. So these are pseudo lines, and they can be made straight if and only if this is a regular zonotopal tiling. And what actually is true in non-dimensions is that the regular fine zonotopal tilings are dual to precisely hyperplane arrangements obtained by shifting these normal lines in generic ways. That's the claim. And I can, yeah, there's a question? No, that here I'm being tricky. I'm choosing these points in a certain way, but in general, I don't think it's possible, or maybe it is. Yeah, in general, these are, in general, these pseudo planes are going to be sort of curvy. So the proof idea here is that, as always with regular tilings, is that you choose a height function. What is a height function? Nice. Yeah. Okay. Right. So I have n vectors, or sorry, m vectors in my vector configuration, and I have m numbers, say 1 through m. So I choose a height function h v r times vi to ai, and then somehow I take the corresponding zonotope. There's this zonotope z tilde of v, which so you lift everything in 1 dimension up, take the zonotope, And then the claim is that the lower faces of this thing are somehow in bijection with regions, or lower dimensional regions, lower top dimensional faces. Dimensional faces of this guy are in bijection with the regions of the corresponding shifted hyperplane. Or something like this, maybe upper faces, something like this should be true. And yeah, I have 4 minutes left. Any questions on this stuff? Now, let me actually say one more thing, which I think I'm going to continue next time, but I'm going to say one spoiler in the next lecture, which is, so let's say you take a graph. You take a graph and then you take the corresponding hyperplane arrangement. Right? Sorry. Take the corresponding hyperplane arrangement A sub G, which is the set of all these hyperplanes where I and J form an edge. So question is, what is the characteristic polynomial of the corresponding hyperplane arrangement in terms of G? Chromatic polynomial. Interesting. Yeah, that's actually true. Yeah, it equals on the nose to the chromatic polynomial. And why, by the way, why was? Yeah, because of deletion-contraction, it actually corresponds to the chromatic polynomial. And yeah, so I'm going to explain this, I guess, next time. But what is actually, to me, what is remarkable about this statement is that, so okay, what is the chromatic polynomial? Right, G of T is the number of colorings of the vertices of G into T colors, where, so assuming T is an integer, non-negative integer, number of colorings into T colors, such that, yeah, proper colorings, such that number of proper colorings. And somehow, this statement actually generalizes to all hyperplane arrangements. You give me any hyperplane arrangement, there is a certain notion of a proper coloring for that arrangement, which I'm going to explain next time. It has to do with finite fields and things like that, but basically, finite fields unexpectedly. Yeah, so next time we're going to do the finite field method, which basically generalizes this statement to arbitrary hyperplane arrangements. And it's a very powerful tool which allows you to compute all sorts of characteristic polynomials. So yeah, I'm out of time. I'll see you all on Monday. Have a nice weekend, everybody.